Okay, so let's go ahead and start this whole thing. And I wish I could just hide all this stuff. It's kind of annoying being here. Okay. There is one thing that might interrupt me. I'm waiting for an email that I might have to answer during class. So that's just something to be aware of. I might have to take a few minutes to answer an email that's quite important coming to me this afternoon. And let's get into MATLAB. I'm still using this older version. I need to update it. But I think I have to update my computer before I update my MATLAB, so it'll take like a day to do the update. All right, so we're back into license update. Okay. Okay. Close. Now I have to restart MATLAB. Sorry. Try this again. Okay. Moving along. Okay, so user-defined functions. We've dealt with a lot of MATLAB functions, a lot of different MATLAB functions that are built into MATLAB. And I think that I've mentioned that there are many functions that you can add to MATLAB. There are add-ons and things they call plugins, which add a lot of functionality to MATLAB, allow you to do a very specified thing. So for example, if you're working on aerospace, there's a specific add-on program that puts a bunch of new functions into MATLAB that are specific for aerospace. They'll have things like Bernoulli's functions and streamline functions and all these other functions where you can calculate things, where you can graph things, where you can manipulate things in ways that are very specific to aeronautical engineering. So, and I think that's my my email that I'm supposed to answer. We'll get started here, and then I'll take a little break and see if I can answer that email. But all of these functions are just little programs that have been written for MATLAB to allow the users of MATLAB to do very specific things. And you, as a user of MATLAB, can create functions like this. They're not terribly difficult to do. Of course, some of the built-in functions that we're used to are things like the cosine. You can use the cosine. You can do the cosine of let's do pi. The cosine of pi, of course, is -1. It knows how to do that. And you can do the cosine with degrees and other things like that. There's just these functions that are designed to do that. However, we can build our own functions as well, but it's going to require some very specific syntax. We have to make sure that we use the correct command code and tell MATLAB exactly what we need to do. First of all, we need to tell MATLAB that we're building a function. MATLAB needs to know that this code that we're about to write is a code that is going to be a new function. Because with functions like the cosine, there's a call sign. We call this a call sign or a function handle, sometimes it's called, where that's the COS. That's the actual thing that tells MATLAB, this is a function and I'm going to use it. And MATLAB knows that when you put in COS, it automatically knows and goes into its function library and grabs the code for the cosine function. And then it also knows that it's expecting for you to input a number in between the parentheses. And it knows all kinds of things about things that you can put into cosine, things that you can't put into cosine, and everything else. And then it knows what to do with that number and what to spit out at the end. So we need to be able to tell MATLAB all of those things and enter all those things into MATLAB for a particular function handle or function name. So we can name functions anything we want pretty much, but we want to make sure it's best to not name functions that we create using the same names that have already been used. So if you remember, that are used in MATLAB right now, for those reserved functions. So if you remember back in chapter 1 or 2, I think we had these different ways of telling, figuring out which names have already been used, where you can use the, I can't remember the name of the built-in function, but it's back on page, it's in chapter 2, I think. Maybe it's chapter 1, I can't remember. But it's in chapter 1 or chapter 2, and it's one of these things where you ask MATLAB, is this being, I think it's, I can't remember these. It's not whose, it's not which, it's not what, it's something. But anyway, you can use there is a thing that helps you to determine whether something is being used in MATLAB or not. You can also just use the help function. So if I go to help, for example, cosine, it has some information about that function. But if I go to help Jared, it doesn't have something for that. So obviously, that's not a reserved function. So you can use that. That's a quick way to decide if something is being used. So I can actually create a function called Jared. And it can be, I can call it with Jared, and I can put in some number for it, 56. And because MATLAB doesn't have anything in there for Jared, then it won't give me anything. It does tell me that there's one called Jared W556. And that's because in one of my folders, I actually have a function called Jared W5, and it's found that on my computer, and so if I go and if I change my current folder to that folder, it should be able to run it. And so anyway, MATLAB has that functionality where it can look for functions that might be script functions. But you do have to be, in order to use that function, you have to have your current folder over here on the upper left corner in my window here. Oosh. It has to be in that folder that I'm in, which happens to be Users Jared Daily Documents MATLAB, and that's not in there. It's in a different place. Well, maybe it is in that. Oh, this is where it is, and this is not. This is week 5. This is not a function. So what it did is it looked for a file that looked like jared.m, and it found this file, but this file just has a bunch of commands in it, a bunch of MATLAB commands in it. And there's nowhere in this file that I've told MATLAB that it's an actual function. I could enter in some code into this at the beginning of this that tells MATLAB this is a function, but I haven't done that. So it tried to execute it. It says right here, attempt to execute script Jared W5 as a function, and it couldn't do it. It didn't do anything. So no good. And it just gave me my prompt back again because it failed. So what is the code that I need to enter in there to make it think that that's a function? That's what we're going to learn today. So we gotta get started on that. So one of the first thing that we have to do, the first part of this syntax, or the first part of creating a function, is to create a function file. And the function file has to be named. So right here in the untitled, I'm going to go ahead and save this. This untitled thing has to be the name of the function that you're going to type in down here in your command window. And so in this case, they want us to call it output. Function output. Let's see, is that it? Yeah. No, sorry, that's not the function name. They want us to call the function name poly. Sorry, I was reading the wrong line. They want us to call the poly for polynomial, short for polynomial. Poly is a name that is not being used in MATLAB. So we can do that. So I save it as poly, and it has to be a poly.m. Here's my format, .m down here. So I go ahead and save that. And now my file is named poly.m. usually the first thing that you put in a function is some comment line about what this function is going to do. So in this particular one, I'm going to say this function will accept let's see, we'll calculate or evaluate, to say, I guess we could say. It's going to evaluate the polynomial, and the polynomial that they want us to evaluate is this one, 3 times x, so it's 3x cubed, 3x cubed plus 5x squared plus 5x squared minus 2x and plus 1. So it's going to evaluate this polynomial here for an input value of x. So we're gonna tell the polynomial what x to use, what number to put in for x, and it's going to calculate it. Pretty simple. You could put your name and the date on it as well if you want to. Most people do. But then we are going to now start the syntax, or start the command code that tells MATLAB what this file is doing, what it is. And the first thing that we do is we say it's a function, and it's easy. You just say function. This starts the function. This tells MATLAB that everything after this line is considered a function. But on this same line, we have to tell it what the function is going to be called and what is going to be input into it. So we always start with something that represents the answer or whatever is coming out of this function. In this case, we just call it output. You can call it whatever you want. Output is a good word because it makes sense. It is what this function is going to output. But the output is going to equal this function when we plug x into it. So this tells MATLAB we're starting a function. This tells MATLAB that the output of this function is going to be called output, and it's going to come from a function called poly, which is the name of our file, and it's going to have one variable that we put into it, which we're going to call x. Now x could be y or z or whatever else. It's just we're calling it x here, and we're going to use x in our function syntax down below. Anything that we calculate requiring this variable that we plug in is going to have to be x, because any number that we put into this function is going to be assigned that variable x while it's inside this function. So that tells MATLAB we're going to start. Now we're going to go ahead and calculate the value of this function, of this polynomial, or in other words, we're going to evaluate the polynomial at the inputted x. So that's right there. So we go ahead and we say that our output, so the thing that we want the answer to be after this function has done its thing, we want it to equal this thing right here, which is our polynomial. We'll just copy that and bring it down here, and then we'll put in some times x and things so that we make sure that it's right. Times x and times x right there. So now all the math is correct, and that's going to be our output. We can go ahead and suppress that output. If we don't suppress that output, it will usually print it twice when we're done, so we suppress the output, and this function will just know that when it's done running, it's going to spit out the answer to whatever number we plugged in, put into this thing. That's what it'll spit out. You can now, at the end of this, you can actually end the function. It's good programming etiquette to end your function. If it's a simple function like this, you don't normally have to do that, but it is good etiquette to do that. And then you are going to go ahead and save this thing. Save it. Now, once you've saved it, you can, and if that's saved in the same file over here that you're using, and it is, it's poly.m right there, saved as a function, then I can go ahead and down here and I can use it. So poly, and I can plug in 7, for example. Poly 7, and run it, and it gives me an answer of 1261. Notice that it doesn't call it output 1261. And notice that over here, we don't have X saved in our workspace, and we don't have output saved in our workspace. That's because within the function, the variable X and the variable output are local variables. MATLAB only remembers them while the function is running, which is a very short time. And when the function is done running and the answer is spit out, it just forgets them. It doesn't keep them.
Mine says it has an error because I used the word and.
Because you used the word end?
Yeah, it says illegal use of reserved keyword and.
Okay, so that may be an artifact of new MATLAB versus old MATLAB. I may not be aware that in the new MATLAB, they may not want you to end your function. And so that could be the case.
I ended mine and it worked.
Yeah. Yeah, I don't know if one person's worked and one person's didn't. I don't know why.
I still get an error.
I'd have to see your code to be able to understand why it's doing that. If it doesn't like you to use end, then just don't use end and see if it works that way.
It didn't. I tried.
Did it work without end?
No.
So in that case, there's something wrong in your code somewhere. So is function spelled correctly?
Nope.
So that will be the problem. If you don't spell function correctly, then it doesn't know you've started a function. And then, of course, the use of end is illegal, right? Because you can't end a function if you didn't start the function. And whenever you're using something like this, whenever you're telling MATLAB to start something new, it always shows up in blue in your M file. So if it doesn't show up in blue, then you've not done it correctly. Is it working now?
Yeah, I forgot to see.
Okay. Yeah, I do that all the time. I always forget the C in my function. It becomes a function, right? Okay. Okay, so that's a very simple function, and hopefully, I mean, immediately as soon as I saw this done the first time, I immediately saw the versatility and the functionality of this. You can put so many different things in here. You can just put operation after operation after operation, and you can do very, very complex calculations and complex maneuvers in MATLAB with the push of one button. You know, you could do just tons of stuff and just have it be one thing, one function. And that's kind of what we'll be doing from here on out. But not only with single functions, but we can do multiple functions, and you can have nested functions. You can have functions within functions within functions. And it can get really complex and complicated, but it can make your work so much easier and better at the end. And that's really what computer programming is all about. Computer programming is nothing more than creating functions that work with other functions, that work with other functions, functions within functions, functions interacting with functions, functions trading off things to other functions. That's all programming is. That's what Microsoft Word is. You know, Microsoft Word, when you open a new document, that's essentially a function. And then when you do things within that document, they're all just functions. And those functions can interact. They can trade things off to each other. They can hand off variables and everything else. And that's programming in a nutshell. So as we get more and more into this and we get better and better at it, we can do more and more stuff, of course. Now, what would happen if we wanted to do this polynomial function, but we wanted to do it with a matrix? Well, I can go ahead and do this, do a save as for this function, and call it polymatrix. Save a new one, call it polymatrix, and then down here, instead of having my output equal to 3 times x cubed, I can do x dot cubed, so that if I input a matrix, it will cube each element of that matrix, element by element. So and then I can do a dot squared there, and I can do a 3 times x is fine, and 5 times x is fine for matrices. So I can leave it like that, and I can go ahead and save it. And then I can plug in a matrix here. I could say, let's say that we're going to do poly matrix of the matrix
You have
to,
to change that up top for your function output thing. Is that supposed to be poly matrix X then?
yes it is. Did I not do that? I guess I didn't. Good catch. So up top in when I call my function, I do need to change this to poly matrix, and it would have told me that. It would have told me I hadn't changed that, so good catch anyway. So I have to save it that way too. Then now MATLAB knows that when it gets down in here to function poly matrix, it is using this M file. This name and this name do need to match, right? Otherwise it won't call it properly. So I use this very simple vector or matrix here, and I go ahead and plug it in there, and it does each polynomial for each one of those things, 2, 4, 5, and 6, right? And then, of course, you're using MATLAB to a higher degree there where you can do multiple calculations simultaneously. And that is hugely important. So, for example, if I am going into aeronautical engineering, one of the things that they do in aeronautical engineering is they measure stress on, for example, the fan blades inside of a turbine for the jet turbine. But each one of those blades, the stress is measured and calculated separately. And each one of those blades has some slightly different things that are involved with it. They turn it, they're rotating into the flow at different times. The flow has different parameters and different dynamics at different times and different places. And so that you can do the same calculation over several different parameters or several different numbers, you could just simplify it as, and get all the answers calculated at once. And you could do 1 million of these, and it wouldn't take hardly any more time than it took to do 4. You know, I mean, it just wouldn't. MATLAB is capable of doing them simultaneously. So, and when you're doing 1 million of these things at once, it really matters. You know, you really want to conserve your time and your calculation power as the best you possibly can. Okay, so that is your very simple script function or user-defined function, as they're called, or whatever. I'm trying to remember, there's another word that MATLAB users often call these functions, and I can't remember what they call them sometimes. But anyway, they're user-defined functions, so you're making your own functions. So let's do example 6.1. Here's an example here that we can do pretty quickly that shows us how this can be useful. And we're going to go ahead and create a new function here. And when you go up here to new, you can actually create a new function. Let's just do that really quick. If I create a new function, it opens a new M file, and it actually gives me this syntax built in, so I don't have to type it in. And you can see here that it has the output arguments, and the output arguments can be a single one like we did, or you can make an array of output arguments. So you can split, if I wanted to make 4 different answers here and split it into 4 different things, I could actually split it into 4 different output arguments. So I could have X, Y, Z, and Q, or I could have answer 1, answer 2, answer 3, or I could have radians and degrees and length and time or whatever. And then you could have multiple input arguments as well. So you can have multiple values to work with, or multiple variables to deal with in your mathematics within the function. And then of course your entitled 3 up here and your untitled 3 down here, those two should match. So it gives you a very nice starting thing where you don't have to remember all the syntax. I like that a lot. So in this one, we're going to be converting between degrees and radians. So we open up a function here really quick, and we want to create two functions, degrees to radians and radians to degrees. One to change it to degrees and one to change, degrees to radians and one to change radians to degrees. And they like to write these things out. They like to write out functions. With simple functions, it seems kind of trivial, but with more and more complex functions, it's very important to learn how to write out functions, how to kind of map them out. And at some point, I think it's actually in a couple of chapters. I'm going to teach you a method for doing that. So let's take a look at our Blackboard really quick and see when that is. Make sure it's not this week. Because I don't want you to be thrown into this without warning. But I think it is in the 8th week stuff. So if we go down here to weekly assignments, now hopefully you're all remembering to leave your functions, tips, tricks, and stuff in the shared document. Hopefully you're still doing that. I haven't checked it lately. I can check it right now. So it looks like we're getting a fair number here. We got a few pages worth. So make sure that you're still doing that each week and leaving your function, your little tips and tricks and the things that you learn, your shortcuts and everything. And we are in week, I think this is week 5 assignment right now.
Yes.
Does that sound right?
Yes.
Okay. So if we go into week 5 assignment, question 1 is your uploaded file, and then question 2 goes right into making functions. Wait, no, week 5 is still graphing. I must have done 2 assignments for week 5.
Must be 6.
Yeah, maybe 6. There might be 2 weeks for graphing, but I don't remember. Let's see, let's go back to week 6.
Yeah, I think that's this one.
I think I'm going to change these to, instead of weeks, I'm going to change them to chapter by chapter. At first it made sense to do them by weeks, but now it's not making so much sense. So here they're doing user-defined functions. So your first question is your lecture notes as usual, but then each question after this is a single file for a single function. So you're going to turn in a lot more files this week. You're going to turn in 9 separate files, 1 for each question, because each one is just going to be a function. You're just going to send me the function, and I'm going to upload your file, and I'm going to run your function. I'm going to plug in some numbers into it and see what happens. So it's a little bit different this week, and then in a couple of weeks there will be a Word file that you have to download, and you're going to do some activities, essentially written activities on how to plan out a more advanced function or a more complicated function. We won't do that yet, but eventually we will. And you can see that on page 209 they do kind of map out their function. They just kind of write what it's going to do. They write what the input is going to be. They write out what the output's going to be. They say that the input will be a vector of degree values, and the output will be a table of converting degrees to radians or whatever. That's a very simple version of planning out your function, and later we'll learn more complicated one. But in this one, we'll go ahead and move on here. So this is example 6.1. We're starting on page 210 now. And we have this table of degrees and radians. 0 degrees, of course, is 0 radians, and then they have the equations for converting degrees to radians and radians to degrees. If you want to convert radians to degrees, you multiply by 180 divided by pi. So they give you all the math. If you're not familiar with that stuff, you can see it all there. But we want to start off with what our function is going to have here in the opening kind of stuff here. And actually, they don't start with that.
Yeah.
They're actually going to start with just the code, the calculation here. So let's go down, and a lot of people do that. That's fine. We're going to go to our command window, and we're going to just test out the code that we need to do to convert degrees to radians. So we're going to clear everything out, and we'll do a little CLC here, and we'll start with defining an array of numbers for degrees. We'll go from 0, and we'll do steps of 15 degrees, and we'll go all the way up to 180 degrees. We're going to go from 0 to 180, so that's going to be our first array of values. And then we're going to go ahead and let's see. Oh, and then we're gonna do our math. They actually do this in a kind of a weird way. I'm trying to figure out what they're doing here. Oh, they actually say in the first part they say go ahead and create those functions, but we didn't create the functions yet. So I'm going to do this in a slightly different way than they're kind of showing it. I'm going to test the math down here, and then I'll put it up in the function. That's fine. The way they do it is just they say create the function, and they don't really show you how it's created. So I'm going to show you how it's created. I'm going to do the math. So if I want to convert degrees to radians, I use the second equation of the top of page 210, where radians equals your degrees times pi divided by 180. So I'm going to say radians equals degrees times pi over 180. Now remember, when you multiply an array times a number or divide it by just a regular number, you can just do the multiplication and division. You don't have to have the dot times or dot divided by. If you do a dot times here or a dot divided by, it won't change anything, but you don't have to have it there. So now I've defined my radians, and if I open up radians, you can see here that it's done that math. 0 degrees is 0 radians, and 180 degrees is 3.14 radians. So that's pi, radians numbers. So that makes sense if you're familiar with that. If you're not familiar with that, your radians vector should go from 0 to 3.14. And then the next thing we want to do is we want to build a table. We want to build our table of degrees and radians, right? So we go ahead and, what do they call it here? They call it degrees radians is their table. So we'll call it degrees underscore radians, or you could call it degrees radians table or dr table or whatever you want to do. And they're saying that this is going to be equal to, let's see, degrees first. So we'll put it into a table where we have, degrees, and then we'll put radians like that. Let's see if that works for us. Nope, that's not right. So we do it this way, we switch it to that, and there we go. Degrees radians gives us degrees from 0 to 180, and then our radians from 0 to pi, right there. And they match up very nicely. So this is the code. These are the lines of code that we need. We need to define our degrees, we need to calculate our radians, and then we need to create our table. And then we need to do the same thing, but something similar for going from radians to degrees. So here's our function. Our output arguments, we'll call our output degrees underscore radians. That's the thing we want to print out. That's our table that we want to print out. Untitled here is going to be called dr. That's what they want us to call it, capital Dr. And our input arguments are going to be degrees. Right? And you could call it x if you want to. That might be easier to call it x. But since we're using degrees already in our code, we might as well use it that way. And then we go ahead and we can write in here what we want our explanation to go here. The explanation of our function and everything else. I'm going to leave that to you to write that in. But then we put in our code here, which is our calculation. Our calculation is the radians to degrees right here. Copy that, put that in there, paste it in. So that's using the degrees variable here. It's defining a new variable called radians here. And then we're going to use both of them to create the table, degrees to radians right here. Copy that in, put that in here. And you could put in some more explanation, some more comment line if you want. Then we end our function. and we save it. Remember that we need to save it using the same name as here, degrees radian, or no, same name as here, dr. So it automatically did that for us because it's set up to do that. That's very nice. Save it like that, and then we go down here and test it. So dr is expecting some kind of array of degrees. And then it will calculate the degrees to radians table. So last time we put in, we could actually just put in degrees here because we already calculated something for degrees and it will just calculate the same table. But we could do a different one. We could do dr of just one number, for example. We could do dr of just 360. What is the radian measure for 360? Right? We plug it in here for 360 degrees at 6.28, which is 2 times pi. Right? And notice that it's pumped out both these numbers because I forgot to suppress the output here. I said that it would do that. So if I suppress the output here, it won't crank it out twice. And then I go ahead and save that. And then I run that again. It'll only give me one table, degrees to radians. So that's kind of nice. Let's see. Degrees to radians. There you go. Gives me just one. There it is. Then you could put any number of, if you just wanted to know a few different ones. We could go degrees to radians. I want to know what it is for 0. I want to know what it is for 23 degrees. I want to know what it is for 46 degrees and 360. You could do that. Oh, it doesn't like that. Why? Because that is actually 4 different arguments. How many arguments did I have up here? Just one. Something we call degrees. So if I want to put in 4 different things, I need to make it an array. Because that's an array is one argument, where 4 different numbers is 4 different arguments. It's expecting to plug 4 different things in, is 4 different variables. It's expecting, when you put in these 4 different things, it's looking for a place to put them. It only has one place to put things, and that's in degrees. So you have to make it an array, then it can plug in the whole array as one thing and calculate them all at once. And that's a very important thing to understand about functions and about MATLAB in general. It treats an array as a single thing, like a single variable, but it treats 4 separate numbers as 4 separate numbers and wants to put them into different places in the equation. And if there's not 4 different variables, there's only one, it's called degrees in this function, then it won't have any place to put them. The radians function, of course, is very similar. Instead of having radians equals degrees, you're going to have degrees equals radians. This equation is going to be different. It's going to be the first equation at the top of 210, and so on. And in fact, what I'd like you to do, I'm going to take a little bit of time to go answer my email. What I'd like you to do in the meantime, while I'm gone for, I shouldn't be gone for too long, but I'd like you to build that other function and see if you can make it work. And go ahead and include the code from that function in your notes file. You won't be able to include the actual M file in your notes file, but include the code for that function, including the introductory code and the end code, of course, and build a function file separately on your own computer and run it and see if you can make it work. Play around with it. If you have time after that, think of a couple other functions you could build. And when I come back, we'll move on and do some more stuff with functions. So play around with functions. I'll be back. Okay, I'm back. You guys succeeded in making another function?
Yeah.
Good.
Yeah.
In the next example, they actually do something a little more complex using logarithms, and then also doing some, they do some figure drawing. They create a chart, excuse me, or a graph. And all that can be done inside of a function. You can do lots of things inside of a function. Let's see here. In this one, they also are creating this function also only uses one variable. So let's actually move on to the next section and create a function with two variables. The only thing really different in the next one that they do here is it's just a little bit more complex of an equation, and then they use that information to just create the graph, and so it's not really that different. The next section is quite different though. Multiple inputs into a function is quite different. So let's go ahead and take a look at that. Go ahead and start off with a clear and CLC. Clean up our window here a little bit, and let's go ahead and look at this. So here's a function, remainder. The remainder function, if you want to, if you remember what this is, it does the division of a number and then gives you the remainder. So the number that I'm going to do is 5. But I'm going to divide it by 3, and it's going to tell me what the remainder of 5 divided by 3 is. Turns out it's 2, right? Can be a very useful function, but it has two things that you have to enter in. It knows that the first thing is your, let's see, what do they call that? The divisor? I don't remember what they call it. But anyway, the thing that's being divided and the thing that you're dividing it by, right? Can't remember which one is which. But anyway, as far as their names go, but that's a two-input function. It only has one output. It only gives you one thing out, but it has two things in. And you can have 2 things in and 1 thing out, or 3 things in and 1 thing out, or 58 things in and 1 thing out, or you can have 5 things in and 2 things out, or 1 thing in and 4 things out. You can have multiple inputs and multiple outputs in functions. It just depends on how you set it up. So if we're going to set up a user-defined function that is going to have multiple inputs, then we open this up here, and instead of putting into this input arguments, instead of putting one thing in, we put in multiple things separated by commas. Okay, so then we're going to do one that looks like just a very simple multiplication function. So we're going to have our output. They're just going to call it output here, and we'll put it as just a single output, so we don't need to have square brackets around it. And we'll call this multiply Jared, just so I know that it's not something we already used. You can use something that is already a function in MATLAB, but it's not good practice because it can be confusing. MATLAB will essentially kind of suppress its own function in favor of your function, and then you're kind of got two functions floating around out there in MATLAB, so it's not a good idea. In the new MATLAB, they might even warn you or something. They probably do. But anyway, we're going to go ahead and have output equal to my function multiply with Jared, and I'm going to have multiple inputs. I'm going to do x comma y, for example. And again, you can call them whatever you want. It can be x1 and y, x1 and x2. It could be a and b, whatever. But whatever you plug in up here are the variables that you have to use down here in your function. Again, you want to put in a summary and an explanation of what this is going to do. Save time by letting you do that on your own. And then we want to have some kind of thing down here. Now in the book they actually say that a is going to equal x times y, and you can just leave it like that, and the user would have to put in numbers. But if they perchance put in a vector or a matrix of some kind or an array, you might want to put in dot y so that it does a term by term or element by element multiplication of that. Go ahead and suppress that output. But because they assigned this multiplication to a variable a, that variable a will need to be assigned to the output. So they say that output equals a on the next line. Otherwise, MATLAB won't know what to do. Let's actually try this out really quick. We'll say that a equals x dot times y, and inside the function it's going to assign a variable a equal to these two things multiplied together. But once the function is, and once this end thing is reached, a will be erased. At least we think it will. So let's go ahead and save that function. And then let's go ahead and use that multiply function, multiply underscore Jared. And we'll put in two numbers, 6 comma 7 for example. So we should get 42 out. We hit return and nothing happens. And that's because inside the function, x dot times y was assigned to the variable a. The variable a is not a global variable. It's not a variable that's going to come out of this function. And so it just gets erased when this function is over and nothing happens on the command window. So if we put in here the output is equal to a, then MATLAB knows what to do with that. We can go ahead and save that. We have to save it before it'll run it that way. And we go ahead and run this function again, and now it knows that the output of that function should be equal to 42 and sets it equal to the answer. Now, I could also do this inside of this function just like this. I could just say output equals, just like we did before, and save myself a line of code, right? Go ahead and save it that way and it will do it. Save that, run the function again, and it's fine. So why would we do it this other way where we save it as a variable? Sometimes you actually want to save it to a variable inside of this function and then use that variable in another calculation within this function. Maybe you want to do multiple calculations, so you don't want to be using output all the time until the answer actually is the thing that needs to be output, because every time you put it as an output, it's going to try to spit something out of the function. So you don't want to assign it to the output until it is the final answer that you want to output from the function. What's your question?
Is there a way to get it to where you put a equals x times y, that it'll ask you what you want for a when you try to run it?
No, because remember when you put something, when you name something here, a equals x times y, you're defining A to be x times y. So it actually knows
Right.
that what A is from there.
So, but when you run a program, you can't have it ask you, because maybe A changes.
So
You
A,
know.
so inside the function, A doesn't have any value until you tell it. So if I put here A equals x times y, then now it knows what A is. Before that, it didn't know what A was. And for example, if I say that A equals 5 here, now the function knows that A equals 5. And down here, I could say that B equals x times y and knows what B is now. And then down here, I could say A plus B, and it would know what that is. And I could assign A plus B to be output. But until you give it an assignment, A and B don't have any meaning to MATLAB.
Okay.
Okay? So if let's say, for example, I put down here A equals 5, and then B equals x plus y divided by A or something. Now it knows what A is because I gave it an assignment up here. But if let's say that I just said A. Let's just say A. And I said A, whatever, and I run this. I just say that. I'm just putting A in. Save this, go ahead and run it. Let's see what it does. It actually doesn't know what A is. Because once I get into that function, A has no value. Even if I assign A here, let's say that A equals 67 out here in my function, in my command window, and now in my workspace, A is a value. A has got this value of 67. And then I run my function, and assuming that it would know what A is, it still doesn't know what A is. Because the function doesn't know this stuff that's in the workspace. The function over here is ignorant of what's going on outside of the function. So it just resets it. So inside the function, you have to define every variable that you use. Now there is a way to pull in these variables out here into the function. We haven't gotten to that yet, and I'm not sure if we actually do in this book. I think we do. But there's a difference between what we call local variables and global variables. The variables that are out here in the workspace are called global variables. That means MATLAB knows about them in general. The variables that we've defined inside of here are called local variables. So they're only known to the function. But if I want this function to understand these variables out here, know what they are, then I have to actually define these variables as global variables. So I think I said these are global. They're not global until I define them as global variables, and we haven't learned how to do that yet. So these ones out here are actually local to the command window, local to here, and they're local to any of the built-in MATLAB functions. So the MATLAB functions know what these variables are, but they're not local to this one. So this one has its own local set of variables, which are A and B and X and Y here. And those are saved separately and locally to that function. So that can get a little bit confusing, but suffice it to say that if you're doing something with MATLAB's built-in functions, or you're just doing some math out here in the command window, it looks to this workspace for its variables. If you're doing something within the function, it has its own little workspace associated with it that you can't see that it deals with. Does that kind of make sense?
Yeah.
Okay. And it can start to get really complicated when you start dealing with local variables and global variables that are passed back and forth in and out of your functions. But as you become a better programmer, it gets easier to understand how that works. I actually, when I was first programming for the first probably 5 or 10 years that I was programming, it confused the crap out of me, and it took me quite a while to get used to it. But again, I'm not a great programmer. This is something that I've always had to work at. So for some people, it just comes more naturally. And it's obvious to me, some of you grasp this stuff pretty quickly because you start to see my mistakes before I see them. And that's good. I'm glad that you do. But usually I have to run something and then I have to see, oh, I made that mistake. I have to go back and fix it. So let's take a look at another one here. Of course, again, with this one that we just built, we can plug in arrays. It understands that you can plug in an array. So if I want to plug in an array of numbers in my first one here, 6, comma 4, comma 5, comma 89 or whatever, I can do that. And I can do an array for the second one too, but I can also leave it as a number. And if I go ahead and plug these in and hit enter, oh, I still haven't fixed my thing back here. So I got to fix my function still. And then I got to fix my function, let's put this as output instead of B. Output. And then save that. And come back here. And it should be able to do this math still because it understands how to do array times number because we've used the dot times in there. So it took every member of this array, 6, 4, 5, and 89, and multiplied each of them by 7. No big deal. And of course you can do as complicated a mathematical thing as you want with multiple inputs. What if you wanted to have multiple outputs? So we can do a function like that. So let's go ahead and make a new function. And I love this new function thing because I think it makes it easier to understand how this works. When I was learning MATLAB, we had to remember how to do this every time. And it was always hard to remember which thing came first and which thing came second, which one was supposed to be your title, but here it makes it obvious which thing is which. I think it's kind of nice that way. In this case, we want to have multiple output arguments for our function, and we'll have, I don't know how many, we'll have one input argument. So our function is going to be titled motion, and they want to have one input argument, which is going to be time. So you put in your little t here for time. And they want to calculate out multiple things, which would be distance is the first one that they want to do. And then the next thing, you put a comma and you put in velocity, which is the next thing they want out. And they're just going to use VEL, and then acceleration. Those are the three things they want to calculate out. And since there are multiple things, it needs to come out in an array. So we put the square brackets around that. That is definitely necessary when you're putting multiple things in. And then you can put in some explanation of this code. We're going to calculate the distance, the velocity, and the acceleration of a particular car for a given value of time. We're assuming all three of these parameters are starting at 0, so that's the explanation you would type in there, and they type that in the book. And then for the acceleration, they actually tell us what it is, so we don't have to know the physics of this. The acceleration is equal to 0.5 times the time, and that's fine. And they're going to do a dot times. Yep, dot times time, and that's fine. So we go ahead and do that. And then the velocity is going to equal the time dot times 2/4. So they're giving us all this information. We don't even need to know the details behind it. And then the distance.
Use a greater than sign in there. It's supposed to be a period.
Yep, sorry. I'm not very good at typing while I'm looking at my book either, obviously. So the distance is going to equal times dot time, no, dot taken to the power of, rather, 3, and then we'll divide that by 12. And we'll suppress all those outputs so that it just gives them as answers. And notice that each one of these is given to one of our outputs, right? Normally we had output here or something like that, but now our output has 3 different names, distance, velocity, and acceleration. And we have a distance, velocity, and an acceleration in our output here. It doesn't matter which order you put them in, but each one of these is a calculation for an actual output. So we just make them equal directly to our outputs, and then we're good to go. We go ahead and save that, and of course it saves as our name that we put in there. And then we can go ahead and put in whatever we want for our time and our motion. Put in 9, for example, and it calculates all 3 of those answers. Let's see, no, it calculated 1 answer. Why didn't it calculate all of them? Let's see here. Which one did it calculate is the question. Oh, let's see. I think it actually only gives us the last one. Does that sound right? So 9 cubed would be 81 times 9 is like 700 divided by 12. That sounds about right. So it actually only gave us the last one when we did that. So yeah, I guess, so when you have three of these things, I've forgotten that when you have three outputs from a function, and this is similar to what we did for, if you remember when we did when we used the function for, what was that function? The mesh grid function. The mesh grid can do a single output or it can do multiple outputs. But when we used multiple outputs, we actually assigned mesh grid to multiple variables. So what we need to do is we need to assign our function here, which is our motion function. We need to assign it to multiple variables. So we go ahead and define an array of variables, and the array of variables that we're going to define are going to be related to each one of these outputs. So dist we'll call distance, and then we'll call the second one velocity. We'll assign that to a velocity, a vector or a number named velocity, and the last one we'll assign to something called acceleration. And then the three values will each be the first one that is put in here. The dist will come out as will be named distance, and then the VEL will come out named velocity, and the XL here will come out and named as acceleration. And then when we plug those in, then it actually assigns them to these separate things. So our distance got assigned to be 60.75, which was the last calculation. Velocity was assigned to 4.5, which is the second calculation. Acceleration, which was the first calculation, was assigned to, the XL was assigned to acceleration as that last number there. So in that way, we matched up each of the outputs with an actual variable in our workspace. So again, it comes down to remembering and understanding how MATLAB works. This function does calculate all of these, but it calculates the first one, and then it may have printed it out, but before it even printed it out, before it even got to there, it calculated the next one, and before that one even got to this window, it calculated the last one, and the last one that it calculated was the one that printed. And if we wanted to print all three, we need to assign all three of them to some variables out here in the workspace so that it actually remembers them. So that is multiple inputs, multiple outputs for functions. Now, you can, and with this one, you could have multiple times plugged in as well, and your answers would come out as, so for example, if we want to know this motion for all of the times between, actually we wouldn't even have to do it that way, we don't know all the times between 0 and 100 in steps of 1, for example, then we could do it that way as well. So our distance comes out as all of these numbers. Our velocity comes out as all these numbers, and that's maybe a lot of numbers to really get a feel for what we've just done. So let's do it in a smaller, let's do it as motion from 1 to 5, maybe, not 1 to 105, 1 to 5. Ah. And then let's do it as, let's actually, yeah, let's go ahead and do that. So for the distance, we get these 6 numbers. For the velocity, we get these 6 numbers. For acceleration, we get these 6 numbers, corresponding to 0, 1, 2, 3, 4, and 5 seconds. Okay. So they do a couple of different examples here at the end of whatever this is, example 6.3. And the examples that they do is one that has a fairly complex equation for metal strength as a function with 3 inputs. So in this case, you have inputs of constant, which is 9600 psi over a square root of minutes, square root of time, I guess. And then you have a sigma value, which is 1200 psi, and then you have a distance, which is a thickness, I believe, which is 1.1 to 10 millimeters in this particular case. And all three of those inputs get put into an equation to calculate something, and then you get a distance out. You get one single output. So actually, that's a good example that I like. However, I actually like the second one better just because it'll take less time to work through. Because it does the same thing, except instead of 3 inputs into a really complex equation, example 6.4 has 2 inputs into a simpler equation, so it's a little easier to understand what's going on. So let's go ahead and do example 6.4, create a new function. And this function is going to be kinetic energy, so we'll call it KE. I don't know what they call it in the book. They call their function KE, yeah, that's right, so we'll call it KE. So the name of our function is KE, and the input for this function, you have 2 things that you have to input. One of them is the mass, and one is the velocity, because kinetic energy equals 1/2 times the mass times the velocity. Now they're going to put in mass and velocity spelled out, and I guess that's fine. I'm not sure I like that much because that means that we have to use those big old words inside of our function, but that's okay because whatever you type in here are the things that you have to use in your function. And I guess that's not the end of the world. The output argument is going to be, they're going to just use output again, and that's fine. That works just fine. You might call it kinetic underscore energy or something if you want to. That might be a little bit more telling. I think I will use that. Kinetic underscore energy. Just because it makes more sense. And then we put our explanation down here, use the equation and everything else to explain what we're doing. But in the calculation down here, we're going to calculate kinetic energy, which is our output. And it's going to be just a single thing here. And that's going to be defined as 1/2. And we're going to do a dot times mass. And we're going to do a dot times times velocity. And the velocity is dot squared, like that. And then we're going to go ahead and suppress that output here so it only prints out once. And then we're going to get some kinetic energies. Now, I think I'm going to do one more thing here. I think I'm going to go ahead and plot something. I think I'm going to plot the kinetic energy and the velocity together. I think that will be an interesting thing. Kinetic underscore energy. And I'll tell you why in the end, and I think we'll actually label the plot. We'll label our x label, and we'll call speed. And we'll do a y label. We'll call damage to your nugget. Okay? All right, so let's go ahead and save this. Should save it as KE, which it does. We'll save that. Then we'll go ahead and run our KE program. We're going to run it with 2 different things. We're going to have mass. So let's say we'll do this for a car. Mass is going to be, for a car, about 1,000 kilograms. We want our mass to be in kilograms. And for our velocity, we want meters per second. So a car's meters per second kind of speed would be 25 meters per second is a pretty good meters per second kind of speed for a car. We'll go ahead and hit return here. And it looks like, oh, we don't get a graph here because it's, why is it not plotting it?
I'm printing something, there's no line.
Yeah, it gave me a plot, but it didn't actually plot the data in it. And I think there's a way to, I think it's because it has forgotten the data in there, and that's fine. And I think that there is a way to do that. Let me look at a previous one that we did here. Okay, so the reason it won't plot inside here, and there is a way to do this. I'm trying to remember what it is, and it's for advanced plot work. But just like the function forgets these variables in here, it actually forgets the data because these variables are the things that are being plotted. So it forgets what to plot in there. So it will make a window. So I've got a window here somewhere, wherever it ended up. I've got a plot window.
Would it be just because there's a single point?
Let me see here. It should show the
There's only
single
one
point.
point on the plot.
It should even show the single point. Let's actually make let's make it a big point and see if it shows up there. If we make this a single point that's a star, for example, that makes it a bigger point. So make it easier to see. Let's see if that works. So it might be because it's a single point, we're not seeing it. Now let's go ahead and run that again. Oh yeah, so you're right. So the single point was just too small to see. So it is showing it. So that's nice. So there's our kinetic energy, but let's do this again for lots of points and see what happens. So we want to do this for a single mass. Let's actually do it for different masses. Let's do it for, let's do let's do from 100 kilograms up to 10,000 kilograms in steps of, no, let's go from 100 to 1,000 in steps of 100. Let's just do 10 of them. Let's see how that works out for us. So if you change your mass, you can see that your kinetic energy increases, but it just increases the same amount every 100 kilograms. It just changes a little bit every time, just like that. So same speed, it just increases your potential energy just a little bit. And it's, I mean, you go up 100 pounds, you go up 100 kilograms, you go up the same amount every time. It does, so the mass doesn't really change your kinetic energy, and it also doesn't change how much it changes how much you're going to hurt your noggin. My plots didn't get labeled here, but I think I have to plot it. I think I have to label them after I plot it, right? I think these have to go down here. I think that's the correct syntax. Save that. Go down here and run it again. Whoa, my computer's wigging out. What is going on? There we go. There's something goofy going on. So if you increase your speed by double, if I go from 100 to 200, I increase my damage to my nugget by double. If I increase it by 10 times, I increase my damage to my head by 10 times. So that's expected, I think. If you have more mass in the car, more damage to your nugget. If you get stopped, you run into a brick wall or whatever. However, let's see what happens if we change the speed. Good night. So if we change the speed, I don't know what my thing is doing here. I'm going to clear this really quick. Clear. And I'm going to do a CLC because something is going goofy in my command window. So now I'm going to go back up here and I'm going to oops. Instead of doing a bunch of different masses, I'm just going to keep the mass constant. And I'm going to change this from about 5 kilometers per hour, and I'm going to go up to about 50 kilometers per hour in steps of 5. I'm going to see what happens as I change speed to what's going to happen to my head as I do this. So here you can see something different happens. If I go from 5 to 10, I have this small change in my kinetic energy. Go from 5 to 15, it's a bigger change, or even 10 to 15, it's a bigger change. So this is actually a parabolic curve, right? So as you change speed and you go from 5 to 50, it's not double. You're going from just above 0 damage to your nugget to 12 times 10 to the 5th damage to your nugget. So the thing that really causes problems with getting hurt in a car is the speed. The faster you go, the much more damage in injury you can go. So if you're going 25 miles an hour, oh, that's no big deal. If you're going 50 miles an hour, you don't have twice as much damage, you have 4 times as much damage. Because it goes by the speed squared. Anyway, nice little function for you there. Let's see, where were we? That was 6 point. Here we actually learn about, well, that's too many pages on. They actually do teach us about local variables and global variables here in this section, so it is in this chapter. We'll get to that in a second. So the next section after this is about functions with no input or no output. You can actually make functions that have everything they need inside the function. They just do something when you tell them to do it. So let's take, for example, one of the problems that we did before, which is creating a star. Remember the function, the code for making a star that you did in your homework, and we did an example. If you write that code into a function, so we open a new function here, new function, and we'll call this function, what do they call it? They call it star. Okay. And we can just leave this stuff out. I think we can leave off the parentheses even. And then we just leave this stuff out. Generally, you kind of leave the parentheses and the square brackets in. I don't know if you have to. Let's see if we have to. And then we put in our code, and if the code is there on page 218, or it's also in the previous chapter. But it looks like this, where theta is equal to pi divided by 2. And remember, we're working in the cylindrical coordinates here a little bit, so it's or polar coordinates as they call it. 0.8 steps of 0.8 times pi, and then the final value is going to be 8 times pi. So we define our theta. We're going to define our r, which is going to equal an array of ones. That's going to have a size of 1 row by 6 columns. So those are going to be the sides of our star. And then we're going to do a polar plot. And it's going to be a polar plot of theta and r. I always do that. Theta and r. Just like that. And then we end that function. And we can save it. Oh, it doesn't know how to do that. So we leave our square, if we leave square brackets in, it means that it's just a null set or an open set. And then we just put in our parentheses here, and it says there's just nothing in our nothing in our input, nothing in our outputs, nothing in our inputs. And then we save it, and then it should save. Now it's saving as star. We go ahead and save that. We'll replace the old one that I wrote before, apparently. And then we go ahead and we just run it, star. Oops, doesn't like that. Theta and rho must be the same size. Apparently I didn't make them the same size. From 1 to 6. And I'm going from pi over 2 to 0.8 and 0.8 pi. Oh, to 4.8 pi. I need to change this. This needs to not be from to 8 pi, but 4.8 pi. That'll give me 6 of these, so I save that. Then I go back to star, and then I can run that program. Now everything's good to go. And it makes a star for me, right? So I just say star, make a star. And there are all kinds of these things built in to MATLAB that are kind of like Easter eggs. Have any of you found any of the Easter eggs of MATLAB?
If you type tick and then talk, it gives you the time between them.
So yeah, here's a function that you type tick and it starts this function running. And then if you type talk, it actually tells you how long it took you to type talk after you typed tick, right? So that's a built-in function that requires nothing in it. And that's actually a very useful function you can use within programs all the time, because then you can actually assign this variable, this elapsed time can be used for something. Any others? There are some, let's go look some up. There are some pretty funny ones out there, actually. MATLAB Easter eggs. Let's go look them up. Okay, so here's a picture of one of the founders of MATLAB that's in there. What MATLAB Easter eggs do you need? My MATLAB is haunted. I love it. It's funny. So MATLAB Easter egg. Let's see. So here's this image that has all kinds of hidden images in it. So here are all the hidden images within this one single image as you rotate it and you change the values in the thing. You know. So let's see, how does this one created? I think, oh, it's just image, yeah. So if you just type in image into MATLAB, I think. So let's see if it works. Image. There you go. And then if you type in all of this other code, you can actually see the hidden images that have been programmed into this image that have been hidden in it, which is quite cool. So here's all the other code that you type in to get that. Let's copy it and try it. Hopefully it's in the same syntax. Oh. Right, type double def image. Shift on identifying function bit rotate. So apparently I don't have the bit rotate function. This bit rotate, if I do help bit rotate, let's see. So that is either a function that my version of MATLAB doesn't have, or it's a function that has changed names and or whatever else. But anyway, you can find all kinds of these things in MATLAB. There is this one's kind of fun. I think I showed this one, load handle, before. Hallelujah chorus. La la la. So penny, this is a nice one. Let's try this one. I've seen this one before, so see if it's still there. Type in, yeah, penny. Then you look at your thing here. It's got this nice three-dimensional image of a penny. Oh, the things that...
Big Bang Theory.
What's that?
I was hoping it was Penny from the Big Bang Theory, but I guess not.
You're a fan of Penny from the Big Bang Theory, huh?
Oh yeah, who's not? From Nebraska.
Uh,
Yeah, live on a farm in Omaha.
Exactly. Maybe it's that pumpkin farm you go to right up here.
yeah, everybody knows that the farms in Omaha are kind of small, right? Little gardens. Anyway. Okay, so anyway, just you don't need, I guess the moral of the story is you don't necessarily need an input or an output. You can define a function without them, and that's perfectly fine. And they do they have lots of examples of these in the book and other places as well. Oh, here's a way that you can figure out how many input arguments there are in a function. If you don't want to just use the help function, because the help function can tell you that as well. But if you type numarg in, number of arguments in other words, of the particular function. So inside your parentheses, in quotes, you put the name of the function, sine function, for example. Number of arguments in the sine function is 1. It wants 1 in there, right? But if you want the number of arguments in the surf function, right, it's going to give you the value -1. What does that mean? If it's -1, then you can have multiple arguments. If you remember, the surf function is the surface plot function. So the surface plot function can receive a single array of numbers that has 2 columns or 2 rows, and it will plot those 2 things against each other. Or it can receive multiple arrays and plot them against each other. But it can also receive other arguments that tell you the color mapping to use, how to plot the points. It can receive arguments about the color mapping to use, whatever. I mean, there's just lots of different things that you can put into the surf thing. And if you look here in the help for surf, you can see how many different things are possible to plug into it. So it's got 1, 2, 3, 4 possible parameters that you could plug in. Whereas if you type in help for sine, there is only one thing you plug into the sine. It's some value that it calculates. Where is the sine? Oh, here it is, sine. Sine of x. It's just one thing. So if you have multiple arguments, it'll give you -1. If you have, and if it's variable, if you can have 2, 1, 2, 3, or 4, or whatever, up to some certain value, then it gives you a -1. You have to go look it up using the help. Otherwise, it gives you this one. It gives you an actual value. And some of them require you have 2 inputs. For example, our one that did the multiplication, it required 2 inputs. It needed 2 numbers to do its math. So it would give you a 2 for that. What was that one called? That was called multiply Jared, right? So if I do number arguments multiply underscore Jared, like that, then it's going to reply with 2 because it requires 2 arguments. So that's a very helpful thing. You can do the same thing with the number of arguments out. It's narg out, number of arguments out. It'll tell you how many of those. So you can use this either way. If it doesn't have a number of arguments, if there's not a number of arguments that is required, if there's 0 arguments in or 0 arguments out, then it will give you a 0. So, for example, the star. Let's do number arguments in for star and see if that works the way we're hoping it does. Yep, so number arguments in for star. Same thing for number arguments out for star. 0, right? So it can do either one. Let's see. Excuse me. Oh, local variables, and on page 221 they create a function that gives you text to the screen out. So if you haven't understood this yet, you can actually assign a variable that is equal to some text, and this is what we call a string in MATLAB. When you have a string, you put a single quote, and you could put, I think they put twinkle, twinkle, little star, right? Twinkle, twinkle, little star. Right? So it actually will print that to the screen as A. A is equal to twinkle, twinkle, little star. If you put that into your function as a variable like that, it will print it to the screen as the answer if it's one of your outputs. Or it will print it to the screen as just as something that prints to the screen if it's not suppressed. So your function can actually print out text to the screen, which, you know, that's useful when you're trying to tell the user something. It might be error, computer is shutting down, or something like that. So one person that I knew that was very good at programming during the programming classes that I was taking, he figured out how to program other people's computers, how to print out things to other people's computers from MATLAB or from other programming things. And so we'd be sitting in the lab and he would access the computer I was on and he would print out things to my screen like, you made a fatal error, your computer's going to explode, or something like this. And it would print out on my screen as some kind of error code with a button that said, press this button if you don't want to die. I was never good enough to make that happen, but he used to do it all the time. So I'd be in the middle of programming code and I'd have to turn around and yell at him for doing that to my computer. Anyway, something to look forward to if you like playing stupid, nerdy, practical jokes on your friends. All right. I could totally see that in an episode of Big Bang Theory, couldn't you?
Yeah.
I could see Sheldon getting a great kick out of it and Penny just looking at them like, what are you doing? All right, so let's go on to section 6.1.6, local variables. And let's talk about local variables, and then we'll get into global variables a little bit. And then we'll move on to some other things, including building a toolbox of functions and what time is it, Hal? We've got some time to finish this up. We may not get all the way through this chapter this week because, well, we might. We probably will. I guess we probably will. All right, so let's talk about local variables. So, like I said before, the variables that you're using inside of the function here to do your calculations, those are called local variables, and they're only used in there. Okay? The input variables, when you have things coming into the function as an input, go back to this multiply function. So whatever the user puts in the first space in the parentheses and the second space in the parentheses, whatever numbers or arrays or matrices they put in there get assigned to these local variables x and y, and then get used down in this code here, and then they're forgotten. And then you have this local variable for output that if you assign something to output, it gets spit out of the function and then it gets forgotten. Those local variables are forgotten once the function has used them. Let's see, what else do they want us to know about? Nothing really. Any variable that you define here inside the function is something that you're going to use inside of here. So this function doesn't have any variables defined except for output, which is one of the function variables. These are function variables which can be used down here as local variables. But you could also define other local variables down here, like when we define the variable A. In the case of the kinetic energy function, we didn't do anything here, but if, let's say that we got down in here and we wanted to calculate, let's say, let's say instead of inputting the mass, we had people input the weight. For example, we had them input their weight into this function, and then down here we actually had to calculate the mass from the weight. So we defined a function called mass, or a variable called mass, which was equal to the weight, W-E-I-G-H-T, divided by 9.8. That would give us our mass, and then so we've defined a function inside of, or defined a variable inside of this function, but this variable can only be used inside this function. If we try to use it out here in the command window won't know what it is. It's only a local variable, only to be used inside here. So if you start defining stuff inside here, make sure it's going to be used inside here, otherwise it just gets lost to the programmer. So this little program knows what it is, but outside of it, it doesn't know what it is. And that's usually how things go. So we could save this, and this would work just fine. But if I wanted to use this kinetic energy function again, and I used 1,000 as my mass, or as my weight, it would define my mass to be 1,000 divided by 9.8, which is like 100 almost, you know. And so it would be giving me the wrong things out. So I'd actually have to enter in my weight now. The weight of a 1,000 kilogram car is actually 9,800 newtons. So I would use 9,800, comma, and then I would put in my velocity, whatever it's going to be, 10 meters per second or whatever. And then I would hit return, and it goes in and it calculates the mass from that 9,800 newtons, and then does the calculation for the kinetic energy from there. So you can have multiple calculations going on inside of your function, but if you're going to define new variables, make sure that they're variables that are just used inside that function. Unless you're going to define a global variable. So this is the new thing. This is page 223. If you want to use a variable that you're defining or you're calculating or whatever inside of this function, and you want to be able to use it outside the function so it shows up here in the workspace, you can do it. But you have to declare a global variable. So in this case, let's say that we want to calculate not just the kinetic energy, but we also want to calculate the potential energy. So potential energy here, I'm going to calculate. And potential energy requires a constant because it's, let's see, it requires, it's m times g times h, so it's mass times the Earth gravitational constant, little g, times h, which we'll call height here. And we'll require one more thing to be put in here. We'll require height to be thrown in here. So we're requiring another input, and we're going to output two things, kinetic energy and potential energy, underscore energy. So we're going to have two outputs and three inputs in our function now. That's fine, that's totally allowed. So in this one, we're going to be using height and mass, but we're going to define this thing g, and we go ahead and define it inside of our function, but maybe we want to use it outside the function too somewhere. So what we do is we declare this variable to be global. We use the built-in function global, or the built-in command global, and that tells MATLAB that this variable is going to be used inside the function and outside the function. So g is global, and then I go ahead and define what g is. Let's see, is that right? No, I define what g is outside of the function. I don't define g inside it. I define it out here in the command window or in some M file that has my code in it or whatever. So inside the function, I'm telling the function to look for g in the workspace. So it's looking for it out here. So I go ahead and save my function here again. And then out here in my workspace, g needs to be known. It needs to be known what g is. G is going to equal 9.8 meters per second, so it's 9.8. I define it here. It shows up over here in my workspace. Right here, g is 9.8. And then I can go ahead and use my kinetic energy function. But remember now, my kinetic energy function has two outputs. So I maybe want to define two variables to plug it into. So I'll define two of them as, my first one is kinetic energy, so I'll call it KE. My second one is potential energy, I'll call it PE. and those are going to be equal to the outputs from this function k, and there are three inputs. Kinetic energy is going to have a mass, or a weight rather, a speed, velocity, and a height. Let's put the height at 98 meters or something, whatever it is. And then I hit return, and it can calculate those things. It only plots one of them because I only made one plot, but it calculates my kinetic energy and my potential energy. Why did it not calculate my potential energy? Let's see here.
You didn't give it an equation for potential, did you? You
I
just said that it's
did. It's equal to mass. Oh. No, yeah, I did that. Mass times g times height. I spelled the height correctly. I did something wrong. Let's global G. Oh, out here I need to also declare global G, I believe. So I have to define it out here, global G. There we go. And then I define G equals 9.8. I have to do it in both places. I forgot about that. And they give you this warning if you've already defined G as a local variable. If you declare it as a global variable, I'm just going to define it again, and then we're good to go. And then I can run my thing here, and now it gives me both variables. So I have to define it in the function and in the workspace, or out in the function window. And then it calculates both the kinetic energy and the potential energy, and we're good to go. Okay, so that's global variables and local variables. The only time you'd use a global variable is in this situation where you're using a number in multiple, you're going to be using a variable or a number like a constant in multiple functions. And you only want to type it once out here and not have to change it within each function. If it would change in each function, you definitely don't want to do that. But if you want one change out here to affect every function the same way so that that variable gets changed in every function, this is a very quick and easy way to do it, is declaring a global variable. Then you only have to change it once out here and you're good to go. So for example, if we wanted to change it to the gravitational constant on the moon, for example, then I could say that G is equal to G divided by 6, which is, I think, about the gravitational pull on the moon. And then I've changed that G everywhere. Now G, instead of being 9.8, is 1.6333, and it's still a global variable. We can go ahead and punch this in, and we calculate our kinetic energy and our potential energy again, and you can see that it changes. The kinetic energy stayed the same because it's not dependent on G, but the potential energy did change quite a bit. So that changes, that shows you on the moon. If you're on Mars, then you could change G again to G equals G divided by 3, which is about the gravitational constant on Mars. And then you could calculate this again and see what it's going to be on Mars, and so on and so forth. So you can see how having a global variable is very valuable. You can make one change and then run a bunch of functions that are dependent on that variable, and you're good to go. Okay. Accessing function code. So in MATLAB, there are some functions you cannot mess with. You can't even see what the code is because they don't want you screwing them up. But there are some that you can access the code you can look at. And I believe you can actually even manipulate the code a little bit. And then save them as a new file. And so one of these So let's actually look at so if I do type, so this is the thing that calls the code, I believe. So if we do type sign, for example, it says sign is a built-in function which will not allow you to see will not allow you to see the code of that function. But there's another one called type sphere. There's another function called sphere, and if you put in type sphere, it actually gives you the code for that function, which is kind of nice. Because now what you can do is you can actually take this code and you could copy it and paste it into another M file, another function file, and you could create a code that is based on this code. You could change it a little bit. You could alter it. You could add to it, take from it, change it in any way you want, and create your new code. And it's a really quick way to make some code. If there is some code out there that is like yours, this is a great way to do it. And I encourage you to do this. I encourage you to find code that will help you shortcut your way to a solution. It's not necessarily easier to do this, because in order to do this, you must be able to understand the code and know how to change it. If you don't understand this code, it could really screw you over when you try to change it, because you'll make one change, you think it's doing one thing, and it does something completely different, completely off the wall. So be careful. However, it is valuable. There is some great value to this. And as you get closer and closer to the end of this class and into more and more complex projects, you're going to want to do this. You're going to want to find a piece of code that does mostly what you want it to do, and then add to it, take from it, combine it with something else, alter it, whatever. It's a great way to write code. This is what most programmers do in their lives. Most programmers do not write code from scratch. They are changing code that has already been written. And that's great. There's nothing wrong with that. It can actually be kind of fun. Then as you start writing code, you can create what they call toolboxes of your own code. So it's essentially just a way of organizing your code and having a way to get at it very easily. You notice that your code, all of the functions that you want to call, or the ones that you want to run in the command window, have to be in the current folder that you're using. However, this is a way, if you put the functions that you want to be using all the time, no matter what current folder you're in, if you put them into a particular folder, or this thing that we call a toolbox, MATLAB knows to look there next. If it can't find it in the current folder, it will look for it in your specific toolbox. And so this is the way that you have to do that. Let's see here. If you look, I think this is actually, I'm looking, oh, here we go. So if we go here, all right, here, okay, so up here in this corner, if we go up here to set path, this will tell you where MATLAB is looking for files, right here. So it's essentially, the first place it's going to look is users, Jared Daly, documents, MATLAB. So that's where it's looking. But there are other places that it looks here as well. It looks for toolbox MATLAB demos, looks under MATLAB, toolbox MATLAB demos, applications MATLAB, toolbox MATLAB Graph 2D, and so on and so forth. So there are lots of places that it will look for things. And if we wanted to look in a specific place, then we need to, let's see here, save workspace, no. From the home, I'm in the right place. I'm not finding the path tool. Anybody see the path tool up here? Let's search for it. Let's see. Okay, so if we go to path tool here, which apparently is under functions, and that's fine. So if we go to the path tool, well, I guess it is underneath this thing. Path tool opens a set path dialog box. Okay, so it is the same one. Okay, they just don't have a button for it up there. On mine anyway. So this takes, this allows us to put functions into a place where they will be used. So let's see here. We want to do let's see if we have any of these things here. We don't have them here. I don't think I've created a toolbox lately. So let's go ahead and create a toolbox. So I'm going to add a folder here, and I'm going to add this folder to the path. Let's see, which one do they use? Add a folder to path. They go to documents and then my functions, and that's fine. So we'll go to documents. And then they're going to create a new folder called my functions. And these folders need to have no spaces in them. Mountain functions, my function. And then we're going to create that folder. Now we've got this folder called My Functions, and I can start to save things into that. I'm going to go to this view, which allows me to see things that I've created maybe a little bit here. Actually, I'm going to go back here, and I'm going to create this in my MATLAB folder. I'm going to create it in here. I'm going to create a new folder called My. And the reason I'm doing this is because then my folders will be next to each other in this view with my function folder is in the same place where all my functions are. So then I'm going to take some of these functions I've created, like the kinetic energy function, and I'm going to put it over here in this My Functions, if it allows me to. It's not going to allow me to, apparently. That's okay, we'll go back here. So I want to save this current path. Go ahead and save that. Now I go down here to my thing here, and I should have my functions here. So there's my functions. And I'm going to put some functions up in there. If I put my area of room function up there, that works. And I can put in my factorial function up in there. So I've got all these functions that I've created. My kinetic energy function, I can put it up in my functions, some of them. And then when I open this up, I've got some functions in there. And MATLAB will MATLAB can go ahead and use those now because I've set a path in my MATLAB search path. I've set a path for it to remember to look for functions in my functions so that I can use that. So that's very useful to have those toolboxes. And you can set different toolboxes for use in different ways, and so that you have them organized. You can say you can call it my aerospace functions or my electronics functions or whatever. You can set different toolboxes, and a lot of programmers like to organize them that way. And when you're creating hundreds and hundreds of functions as a programmer, of course, organization can be extremely useful, especially when those functions are going to call each other. You can have one function that actually uses another function within it. Functions within functions. Okay. We're almost out of time here. There are two other things that we need to talk about really quick, and three other things really. And that's the use of anonymous functions. An anonymous function is a way that you can write a function within your command window. And they actually show you how to do this on page 227. And so, for example, if I want to create a new function called the ln that is a function that uses another function that's built into MATLAB, I can say that ln is equal to, and then I use the @ symbol. The @ symbol is gonna say that I'm creating a function that's just going to be made temporarily in the command window, and it's called an anonymous function. So they use the @ symbol for anonymous. And then I tell it the variable that I'm going to use within that function, and then I write the function. I write the actual functional math. So it's going to be the log of x, for example. And I'm going to create that function now here. And then when I've done that, it knows now that ln of some number like 98, for example, or 90, is going to plug this number into the function log of x. And then it does the math. And you can make this whatever you want. If I do that again, and I do it now the sine of x, it now creates a new function. A new function is now you plug whatever number in for the sine of x, and now ln 90 gives me a completely different answer. It's actually taken the sine of that number that I've plugged in. So those are anonymous functions. And anonymous functions are useful when you want to just create a quick function that does something really quickly and then use it over and over again. But once you clear this out, once you clear out and notice that this anonymous function shows up over here in your workspace, but once I clear my workspace, it forgets it. So that can be useful for just short functions. Lots of things are done that way. You can also save those anonymous functions by using the save save command, and it will save it as a function, a real function. But they do have limited usefulness, but they can be useful for quick things. Also, oh, by the way, when you do this, the thing that you assign it for is called the handle. So very similar to real functions, they do call that a handle. Also in section 6.5.1, they talk about subfunctions. And subfunctions, again, can be very useful. I don't know that we're going to actually use them. I tend to... I'm trying to remember if we do use them later on. But essentially, subfunctions are functions that you write inside of another function. So you're creating a function file, and then you create several functions within that file. And again, can be quite useful, and I think we do use it when we start doing graphical user interfaces. So we'll get some more practice with them. But it's just writing multiple functions within one function that can be used together. In other words, they can all use the input arguments from the outer function, but each one of these inside functions can do different things. So the syntax is essentially the same for a normal function, but it's just multiple functions within a function. We're running out of time, so we don't have time to go over that. We've got to turn this off here in a few minutes. But probably the best way to understand how this works is to look at the example of a subfunction on page 234. And there's also 229. They have this here, where you have the main function that starts off by bringing in some variables from the user, but each function underneath it can use those x and y variables to create different things, and then those functions can interact to multiply or to divide or to do whatever. They can do all kinds of calculations or create different graphs, and they can pass things back and forth. And so it gets a little complicated, but that's the whole idea, is to do something more complicated using multiple functions within one function. But they're all using the same local variables that were passed in by the user. And they will all eventually pass things to the main function so that the main function can pass the output out to the user again. So each function within the function may have different inputs and outputs, but the main function, that is the first function put into that overall function, is the only thing that can pass things out to the user. So hopefully that made sense. When we actually use it later on, we'll point out all these features and how they work together so that it makes more sense for you. But they've just trying to give us as much about functions as possible here. And I don't remember if I gave you something involving subfunctions in the homework. But if I did, it shouldn't be too hard for you to crank out. Because I wouldn't have given you anything too advanced. So, does anybody have any questions before we turn this off? Because somebody else wants to use Zoom here in a few minutes.
So when we turn in our homework for this section, do we have to attach all our KEs and
Yes.
RDs and DRs?
Each
Okay.
Each problem that you do will be a function file that you will turn in, and that's it. It will be a
No,
function.
I mean for our homework for question 1, if it's running all these codes, do you have to have those files?
Oh no! So for your homework for your notes for class, you'll just turn in the stuff as you normally have turned in a single M file. But
Okay.
when you turn in your homework, each individual problem will be a different function file.
Right.
Okay? Any other
Okay.
questions? Okay, well, we're done for the day, and have a good week. If you have questions, remember to email me or call me or contact me otherwise, and have a good one.